In this video, you will see a visual representation of different sorting algorithms using two types of datasets and a performance analysis which highlights the pros and cons of each technique. We are analyzing 5 sorting algorithms: insertion sort, selection sort, bubble sort, merge sort, and quick sort. For this experiment, we have used two types of datasets. The first dataset is a randomly generated array of 500 positive numbers, and the second dataset is an inversely sorted array of 500 positive numbers. Bubble sort. Bubble sort is a simple sorting algorithm that repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. The pass through the list is repeated until the list is sorted. The algorithm, which is the comparison sort, is named for the way smaller or larger elements bubble to the top of the list. Bubble sort is a stable sort which has a complexity of O of n square, whereas in the case of nearly sorted data, bubble sort takes O of n time. Insertion sort. Insertion sort is a simple sorting algorithm that builds the final sorted array one item at a time. At each array position, insertion sort checks the value against the largest value in the sorted list. If larger, it leaves the element in place and moves to the next. If smaller, it finds the correct position within the sorted list, shifts all the larger values up to make a space, and inserts into that correct position. Insertion sort is a stable sort and it has a worst case time complexity of O of n square. Merge sort. Merge sort is one of the most used comparison-based sorting algorithm. Merge sort is a divide and conquer algorithm, and I will explain how it works. First, it divides the unsorted list into n sublists, each containing one element. A list of one element is considered sorted. Then it repeatedly merges the sublists to produce new sorted sublists until there is only one sublist remaining. This will be the sorted list. Merge sort has a complexity of O of n log n. Quicksort. Quicksort is a widely used divide and conquer based sorting technique. Quicksort first divides a large array into two smaller subarrays, the low elements and the high elements. Quicksort can then recursively sort the subarrays. Quicksort is not a stable sort and it has a time complexity of O of n log n. However, in worst case, the time complexity of quicksort is O of n square. Selection sort. The selection sort algorithm sorts an array by repeatedly finding the minimum element from unsorted part and putting it at the beginning. The algorithm maintains two subarrays in a given array. Initially, the sorted sublist is empty and the unsorted sublist is the entire input list. The algorithm proceeds by finding the smallest element in the unsorted sublist, exchanging it with the leftmost unsorted element, and moving the sublist boundaries one element to the right. Selection sort is not a stable sort and it has a time complexity of O of n square. We observe the following regarding the different sorting algorithms. Although bubble sort is simple, it is slow and impractical for most problems when compared to insertion sort. Bubble sort can be practical if the input is in mostly sorted order with some out of order elements nearly in position. Insertion sort is less efficient than the more advanced algorithms such as quicksort or merge sort. Insertion sort is the algorithm of choice either when the data is nearly sorted, as it will run in a linear time O of n, or when the problem size is small because it has low overhead. Merge sort takes O of n extra space to sort. If using O of n extra space is of no concern, then merge sort is an excellent choice as it is the only stable sorting algorithm running in O of n log n time. As you can see, for both the datasets, random and reversed, the average time taken by merge sort is the same. It will run in O of n log n time irrespective of the degree of sortedness of the data. Quicksort's efficient implementations are not stable, meaning that the relative order of equal sort items is not preserved. Hence, it is an excellent choice when order can be ignored. Selection sort takes O of n square comparisons and O of n swaps. However, it has the property of minimizing the number of swaps. In applications where the cost of swapping items is high, selection sort can be the choice of algorithm.